Hello everyone, we are pleased to present our research work on post-form arches and more precisely on building crossings in wicker, flexible construction of a post-form footbridge in active bending stiffened during service phase. To contextualize our research, we designed a footbridge for the first edition of the Utopies Constructives festival, which will take place in springs 2023 in the city of Richelieu, Indre-et-Loire, France, organized by the Beta. For this occasion, our team of students from School of Architecture Paris-la Villette and CentraleSupélec, with teachers from Construire l'Architecture, have designed a 12.8 meter span footbridge built in wicker. Wicker is a natural fiber collected once a year during winter, which can reach 3.5 meters by young willow cuttings. It's a very minimal cultivation requiring limited inputs maintenance, water consumption and CO2 emissions. Nevertheless, in France, the amount of willow plantation has drastically decreased from 25,000 in 1890 to only 400 during the 90s. The department of Indre-et-Loire, where our project is realized, undertakes action for the conservation of this craft. Basketry has emerged very early in human history. The first traces of wicker objects date back to the Sumerian civilization, 4000 before Christ. And the first traces of basketry were found in Fayum, in Upper Egypt, around 10,000 before Christ. Everywhere on the planet, people began to weave natural fibers for the design of objects, clothes or shelters, thanks to local raw material and local know-how. Architecture and construction have slightly opened their doors to the heart of wicker work, but it's mostly limited to non-structural feeling. Since 2021, a team of students and teachers from School of Architecture Paris-la Villette and CentraleSupélec has been developing the Baya project, an algorithm created to optimize the braiding of structural shells for architecture. We were so able to identify obstacles to our crossing project. Durability, like timber, wicker is sensitive to UV, moisture, fungal and wood-eating insect attack. Elevability of the material, which is creeping and becoming more brittle with time. Node slipping. Since Baya experiments, we know that the nodes of a full-scale project are slipping at each use, causing deformation of the structures under load-unload cycles. Likeness. Usually, an arc must have a predominant self-weight in comparison with the live loads. To develop a braided wicker footbridge, we follow general construction method based on the construction of post-form elastic gridshells. The object is first made by braiding the wicker flat and flexible. Then it's shaped by buckling thanks to the tension in ropes connecting the legs. Finally, the shape is stiffened for the service phase by stitching together the railings, forming a structural U shape 1 meter high by 1 meter wide. The Baya algorithm determines the principal stresses for any shell under a given load. Thanks to the above optimal braiding laws, it's able to give the ideal braiding for the shell. Algorithm can be applied to any loaded surface, including basketry items. We have chosen to illustrate its presentation on an isostatic beam and two supports loaded by a uniformly distributed force. To determine the laws of an optimal braiding, we conducted numerical simulation by dynamic relaxation to study the reaction of a braiding specimen subjected to a field of principal stresses in compression and tension. The objective was to understand the influence of the different parameters such as value of the force in each direction, braiding densities and orientation. The shell surface, the position of the support points, and the loads are the input data of the Baya algorithm. The surface is discretized into small rectangular isosceles triangles, each representing a finite element of it. Then we calculate efforts in the finite element edges by dynamic relaxation, and we deduced from it the principal stresses in the finite element. By using the laws defined previously, we eventually obtained the optimal braiding of the shell. The algorithm can be applied to any loaded surface, including baskets, isostatic beams, shells, and thus also footbridges. Here is the plan of an optimized braiding arc forming our crossing project under a force of 400 kilograms uniformly distributed over the project. Once we manage to demonstrate the constructive feasibility on small-scale models, we compare our structural design to the results of our experiments. This step is necessary because Baya does not take into account a certain number of parameters, such as knot slipping, buckling, overturning, and the calculation of the deflections. Therefore, we built a 1/5 scale model and tried to anticipate the structural failure modes that could ruin the footbridge. We have selected 5 of them in the first instance. M1 is wicker failure by traction. M2 is wicker stress failure by compression. M3 is local wicker failure by buckling. M4 is failure by global buckling. And M5 is warp failure by traction. M1, M2 and M3 is failure modes are normally taken into account by Baya. We have calculated them with a maximum load equivalent to the weight of 4 people on the real scale footbridge. It's important to point out that these failure modes are very sensitive to the variations of the position of the funicular in relation to the neutral fiber of the section. We then run loading tests on the model, adding at each step 4 kilograms concentrated at the center of the arc, modeling live loads, and 4 kilograms uniformly distributed, modeling additional dead loads. The deflection at the center of the bridge is measured at each increment. At 12 kg, the bridge was fully unloaded and the deflection measured. The loading continued in the same way until failure. When then run a second test with the loading concentrated at the center. The results of these first 2 loading tests are: as designing, the 1.1 footbridge should support only 1 person's weight of 94 kilograms. The failure is due to overhaul arc buckling, the only one that we could not precisely forecast by calculation. The hypothesis of classical arc failure mode is challenged by the fact that wicker is capable of resisting to tension, unlike a masonry arc. In this context, the experience showed that the ballasting of the footbridge is not an asset. In order to increase the load capacity of the structure, we decided to add anti-buckling bamboo tubes between the deck and the ropes. A second loading test is carried out on this new design. We note that, once modified, the footbridge should be able to support the weight of 2 to 3 people, so approximately 220 kilograms. The main difference with the numerical prediction, 400 kilograms, is that in the numerical prediction the load was divided into 4 loads of 100 kilograms, almost uniformly distributed on the length of the footbridge. Therefore, the physical model confirmed, rather correctly, the Baya numerical model. The failure mode is M1. The failure occurred on the extrados at a stitch between module 1 and module 2. The local traction is maximum close to the base of the arc as it is expected in a classic masonry arc, because the position naturally taken by the funicular is an arc, that's a passive thrust. A rounded braiding wicker and rail will be added to the scale 1-1 to take up the traction on the extrados more efficiently. After these studies and experimentation, we have begun to build the footbridge at 1-1 scale. The construction is divided in 3 phases. The first phase is dedicated to the construction of the 6 parts of the footbridge, following the plans provided by the Baya algorithm. The second phase is dedicated to braid a link between the 6 parts to shape by buckling and to reinforce the interruption in the railings and stitch it together. The third and last phase is dedicated to the finalization of the structure by adding the final levels of wickers until we got 500 kilograms of wicker, and to build a rounded braiding wicker handrail to increase the structural resistance. We already advanced to the third phase and we hope to finalize it since the end of the year. To conclude, our footbridge used 500 kilograms of material and it's made of 90.1% of wicker. In order to make a 100% wicker footbridge, we should explore a tubular shape, more wide and therefore more stable regarding buckling. At the end of the 1.1 scale construction, the data will be analyzed to develop innovation of Baya, capable of the calculation on global buckling, on the deflection and to taking into account the slip of the braiding nodes. After that, the contributions of the study of the wicker crossing will be transposable to other structural shale projects for architectural use. We would like to conclude this presentation by thanking all the contributors who have taken part in, and all our partners who have contributed to the success of this work. Thank you all.